This tutorial focuses on futures modeling of SE systems. I will briefly describe the features of SE systems that make analyses of the future difficult, review the overarching issue of purpose, what is the point of a modeling exercise, and then describe three main approaches to futures modeling for SE systems. I'm not going into specific modeling techniques, like ABMs or dynamical systems, because many of these different technical modeling approaches can be used for futures models. Socio-environmental systems, known as SESs or SE systems, involve the interactions of humans and our environment. SESs are really systems of systems, with component environmental and human systems that have internal dynamics and complex interactions between them. System of systems or multi-system models are often employed in SES modeling. In the human system, resource users, that is, people, make decisions that depend on other people or groups. Together, these elements of the human system are called agents or actors. These can be groups, people, or even institutions. These agents may be constrained by policy, which is the result of individuals making decisions in aggregate, for example, through democratic processes. All of these actors within the human system affect and are affected by the state of the environment. In the environmental system, biotic interactions and feedbacks also occur, for example, during nutrient cycling or ecological competition. These processes result in a range of feedbacks that occur at varying time and geographic scales. Generally, feedbacks and changes at the policy level are slow relative to changes in individual human behavior. Environmental feedbacks involve fast and slow processes. The purpose of a futures analysis or modeling exercise may vary greatly, from a broadly attended workshop to promote discussion to exploring projected consequences of policy options in an effort to formulate a favored policy robust to future uncertainty. At other times, the purpose can be forecasting the probable state of a system, or even providing a real-time operational forecast that aims for quantitatively accurate projections of the future system state. Different purposes may entail different time horizons. For example, a near-term horizon for this ensemble forecast of a disease. Other purposes may entail quite long timescales. For example, using futures analysis to discover potential future states. Besides timescales, analyses with different purposes may take very different approaches to human actions and decisions. Different purposes also imply differing approaches to uncertainty. One way to organize techniques for analyzing the future of a socio-environmental system is along a spectrum according to the degree of uncertainty considered. This categorization comes from the Dutch policy analyst Warren Walker and co-authors. The techniques range from probabilistic forecasting at the low end of uncertainty to qualitative scenarios generated without reference to particular quantitative models or to criteria at the highest level of uncertainty. In between these extremes lies a challenging terrain for socio-environmental futures. Here, quantitative biophysical models must be integrated with human decisions and responses to our environment. In this tutorial, I will describe three main approaches for futures analysis in SE systems, organizing them by their approach to uncertainty. These include qualitative scenarios, quantitative scenarios, and forecasts. I will use examples to illustrate these categories. First, qualitative scenario analysis, or scenario modeling. The main purpose of scenario modeling is to discover possible futures without need for defined quantitative models. Developed in military and corporate settings in the latter half of the 20th century, scenario modeling, sometimes also called scenario planning, is a way to deal with both strong feedbacks among system elements and the potential for wildcard or extreme events. In socio-environmental systems, this could be land use change triggered by mass migration of people, or devastating natural events like tsunamis that displace people and destroy valued ecosystems. In examples like these, qualitative scenario planning involves groups of people developing conceptual models and laying out responses to anticipated future changes in the driving environmental and social variables. It results in narrative and often visual descriptions of future states or scenarios. Now for a detailed example. I'll discuss an application of qualitative scenario modeling conducted in 2002 for the Wisconsin Northern Highland Lakes District, or NHLD. It's associated with a beautiful wooded landscape covered with many lakes. As is typical, the scenario modeling exercise was conducted by a group involving a range of stakeholder perspectives. The North Temperate Lakes Long-Term Ecological Research Network, or LTER, did this scenario planning as a group exercise to get a range of stakeholder perspectives. Conducted in 2002, the exercise focused on ecological outcomes under both changing climates and unknown economic and social changes. Participants developed a conceptual model that linked drivers, in gray, to human actors or agents, people and institutions in green, and the decisions made by these actors, for example, land use decisions labeled linkages, to ecological outcomes. The drivers here may be both biophysical, like geology, human, like migration, or a combination, like climate change, mercury deposition, or biological invasions. The outcomes considered here were ecological, what are now called nature's benefits to people, or ecosystem services, fishing, water quality, aquatic ecosystem condition. But the analyses also examined access to and distribution of these benefits. The role of people in our institutions is key, and the analysis was more complex than this single box reflects. The exercise considered the interactions and preferences of local residents, visitors, and different governments, like municipal, county, and tribal, with regard to the biophysically mediated impacts. The group considered system responses to anticipated social changes, such as population growth and economic change, and exogenous environmental changes, such as climate warming. This exercise teased out two major axes of variation: speed of ecological change and intensity of local development. The axes had different implications for the existing gradient of variation in development, from pristine to highly impacted, in the Northern Highland Lakes District. Several scenarios were developed, each envisioning outcomes across a range of pre-existing or baseline lake development. Walleye commons, where the ecosystem degrades but human population density remains similar to baseline. Lake Mosaic, where the local economy shifts towards tourism, recreation, and retirement. And Northwoods.com, where the local economy shifts towards the tech sector, which results in migration and local wealth but more protections for lakes. In summary, qualitative scenario analyses like these require a range of opinions and perspectives, a synthetic conceptual model, or time to develop one, and the ability to use narrative scenarios. Scenarios can also be used in quantitative analyses of the future, and in fact, they can be used to envision a multiplicity of plausible futures. Such futures are necessarily grounded in biophysical models and define pathways from the present to the future state, which is in contrast to qualitative scenarios where anything is possible. The purpose of quantitative scenario analyses might be to evaluate policy options over a wide range of plausible futures, or even design policies that are robust to all futures that are considered plausible. As with the qualitative scenarios, I will illustrate the key features of the quantitative models with examples. These key features include the ability to examine quantitative variation in outcomes across changing policies and changing extrinsic drivers. Generally, this requires at a minimum several distinct models of the future with different structures, not simply a range of parameter uncertainty in a single model. Alternatively, several possible policies can generate a set of quantitative scenarios for input to a single model. For example, water demand in the Emirate of Abu Dhabi is high and increasing. As part of a multifaceted scenario analysis taking into account the water needs of different sectors, Mohammed et al. 2020 evaluated the impacts of 4 different water management policies. Here, I show the results from 3 of these. The colored bars are different sector uses. The y-axis is in units of million cubic meters of water, but focus your attention on the lines that are labeled on each graph. You see very different quantitative outcomes. In the business as usual, groundwater continues to be used heavily, so the amount in reserves drops significantly over time. In the middle graph, where some sector allocations are reduced, we see that groundwater use declines until 2030, but then levels off. So while reserves decline, they do so less than in the business as usual case. Obviously, the best scenario in terms of reducing risks, that is, having more groundwater in reserve as shown in the rightmost graph, is the one in which water from the ocean and from increased rain supplement supplies. Another more familiar example is the Intergovernmental Panel on Climate Change's Representative Concentration Pathway, or RCIP scenarios, for carbon emissions over the coming decades. Obviously, each of these scenarios has implications for humans, but also assumes specific human behavior and policy decisions. For example, lower concentration RCPs assume reduction in energy use or substitution to less carbon-intensive types of energy. Scenarios also examine outcomes across different policies, as seen in the groundwater example. Yet another example is the following analysis of ecosystem-based management of fisheries, which considered different policies for allowable catch not only of cod, but for another fish, haddock. But fishers might change target fish based on policy changes. For example, if the haddock fishery was closed and so some boats might switch to fishing for cod. Because of this, a systems model including both species that accommodates and interfaces with policy changes was contemplated. Here is the conceptual model developed by the National Oceanographic and Atmospheric Administrations, usually referred to as NOAA, for the Gulf of Maine and the northwestern Atlantic Ocean. The resulting projections under different policy scenarios showed that the catch policies considered produce variation in the projected standing stock biomass of cod. A medium-term, weeks to months example of policy-driven scenarios is the plausible futures of a pandemic disease. For COVID-19 in winter 2020 to 2021, the Institute for Health and Metrics and Evaluation, or IHME at the University of Washington, considered several scenarios centered on how different states and localities employed mask use and social distancing mandates. Combined with IHME's statistical curve fitting model that projects epidemic curves based on past behavior, these scenarios resulted in a 10-fold variation in projected deaths per day at the peak of the winter pandemic wave. When scenarios contemplate variation in drivers of human behavior, these could be translated to system behavior, but this requires a human decision model. If you aren't familiar with these models, they simply refer to models developed to describe the decision-making process and how it interacts with other dynamic components. I'll use a land use change case in Belgium to illustrate how variation in drivers over time influence changes in flood risk. In this case, several models were coupled. The group used a system model that included as a driver an externally specified rate of urban expansion. Such expansion is of interest because increased infrastructure and population size in urban areas increases damage due to flood exposure. Several rates of expansion, including low, medium, and high, were fed into an agent-based model of human economic development that considered the responses of planners, developers, and existing residents. In the scenarios, developers made various decisions on where development was to go. Planners had to give permission, and residents could resist the decisions. Feedbacks in this model captured both urban expansion and increased infrastructure within the existing urban footprint that could heighten the risk of flood damages. Together, this effort yielded scenarios for future development trajectories of both expansion and infill development under varying land use policies with, as shown here, the resulting effects on 2050 flood risk varying considerably. So, thus far I have illustrated that qualitative techniques can allow us to explore many possible futures, while quantitative techniques require clear pathways to plausible future states. Now I will shift to using both qualitative and quantitative techniques for scenario analyses. The purpose of such a combined approach would be to evaluate management options over a wide range of plausible futures, beyond those we could quantify using existing models. An example of this which I'll mention is evaluation of a fisheries management strategy. A quantitative scenario analysis could serve this purpose as well, but we might turn to a combined approach if there are not yet existing quantitative models for the scenarios contemplated. Two approaches are possible. First, we can seek to translate qualitative scenarios into quantitative outputs or models, and there are a variety of methods for this. Second, rather than a computer model for the human decision processes involved, we can use real-world simulations or games. These can combine both computational and human decision-making. In the first case, we require translation of qualitative or narrative scenarios into parameters and states of quantitative models. A variety of specific techniques exist for this, including causal diagrams, fuzzy cognitive maps, and Bayesian belief networks, just to name a few. We also require modeling human behavior and decision-making in response to changing conditions in the scenarios. This could be done through computer simulations. One means for such computer simulations is the use of agent-based models, such as the one shown here modeling interactions and decisions among agents representing various stakeholders in conservation and development, including agencies, developers, farmers, and foresters. A completely different way to approach the problem of human behavior is to game out or simulate response via actual in-person stakeholder interactions and engagement. This is similar to a war game, as practiced in national defense or disaster preparedness contexts. While quite resource-intensive, a version of this, called management strategy evaluation, is best practice in well-managed fisheries in the US and worldwide. Management strategy evaluation exercises focus on a particular ecosystem and the fisheries it supports. They involve intensive stakeholder engagement and participation to define objectives and determine indicators of success, as well as to interact in real-world simulations and finally judge outcomes. While many of these exercises do involve stakeholders and in-person interactions to game out scenarios, that is, to decide stakeholders' probable economic or social response to simulated conditions, some of the human responses could also be computationally simulated. However, meeting realistic decision-making timeframes often does not allow for implementing complex human behavior models. For example, in an MSE for herring in the Northwest Atlantic, a closed-loop simulation model, shown in this diagram, was developed with stakeholder input. Output from the model was then used interactively in the MSE exercise. Note that while there are economic dynamics and biological dynamics, including models for the effect of the fishery on important herring predators like birds and whales, the potential economic spillovers to other fisheries, for example through entry or exits of vessels, are relatively complex and were not modeled directly in the closed-loop simulation. But, during the interactive MSE process, such effects could be considered by stakeholders in their evaluation of potential control rules. In summary, quantitative scenario modeling requires one or more quantitative models in the first place. Then one needs to express scenarios within the model, that is, through parameters and specific functional forms. An advantage of this approach over qualitative scenarios is it yields quantitative projections that can be more concretely compared to data and/or numeric policy targets. However, a set of quantitative scenarios may not capture as much uncertainty as blue sky qualitative scenarios. Combining qualitative scenario development with quantitative projections can draw on strengths of both approaches, but may be the most time and resource-intensive approach of all. Turning now to forecasts, which are inherently quantitative. The main purpose of these analyses is to provide projections of the probable or likely state of an SE system at a defined point in the future. This is different than scenarios, which focus on many plausible futures. Forecasts are conditional on assumptions about trends in economic or social factors, such as population growth or consumption patterns. They're also conditional on assumptions about policy as well as environmental conditions. Among the most familiar are forecasts of future socio-environmental states under specific assumptions regarding climate change and economic activity. To produce quantitative forecasts for SE systems, practitioners turn to three main techniques: using ensembles or set of forecasts from different models, limiting their forecasts to short times, known as short lead forecasting, or using data assimilation or other techniques to update their estimates, as is done in weather forecasting. Ensemble forecasting is used in practice by the U.S. National Oceanic and Atmospheric Administration to forecast the extent of the hypoxic zone in the Gulf of Mexico based on the observed mean May nitrogen load in the Mississippi River. Nitrogen load has varied considerably since the 1980s. This graph from a study by Scavia and colleagues shows three forms of nitrogen in the Gulf over time. The black line indicates biologically available nitrogen, which is most important in causing hypoxia. This graph provides data on the relationship between reductions in nitrogen moving to the Gulf in May and the size of the hypoxic region. Notice there is a relatively tight correlation. An ensemble of statistical and mechanistic models of the biophysical system, shown as different line types here, feed into NOAA's operational forecasting model for the maximum hypoxic area during summer. The models used in the ensemble differ in their assumptions and approach. Some are statistical, like multiple regression, and some are biophysical models, such as models that solve a mass balance equation based on biophysical conditions. This is an operational forecast produced and used by NOAA and described in this informational pamphlet. The Gulf of Mexico example features both an ensemble and a limited timescale, that is, a short lead. Any forecast of more than one season would have to incorporate long-ranged climate forecasts as well as the potential for changed human behavior over this time. This is true especially because these forecasts from NOAA are used as outreach tools by state and agricultural bureaus for nutrient management. Over longer timescales, there could even be the chance people could respond to the forecast and change their behavior. The NOAA example modeled only the biophysical system and chose a short timescale where the human system need not be modeled. Models of full SE systems of systems may make very different assumptions about policy and the human system, but using ensembles and short timescales together can still enable accurate forecasts. I will discuss short lead forecasting in more detail later, but first, another example of an ensemble forecast. The COVID epidemic in the United States provides a good example of ensemble forecasts that include human behavior. Pandemic disease forecasts can either assume the current policy and government interventions remain in place, or that they change based on various rules, for example, assuming increases in activity restrictions as cases increase. This results in large disagreement over even short, say, 4-week timescales, as in this forecast of new weekly U.S. COVID-19 cases in the fall 2020 from the COVID-19 Forecasting Hub. Note the wide variation in projections, which is a result of including models that both are conditional and unconditional on social distancing policies remaining in place over the forecast period. Despite this variation, averaging expectations over many models can give relatively accurate forecasts. Here, only a single ensemble forecast combining all previous shown forecasts is shown, as well as the actual trajectory of cases during early December 2020. Aside from the near-term epidemic forecasting, fisheries are another area where short lead forecasting within a season or during an event has proved successful. In Bristol Bay's famed sockeye salmon fishery, management is for a set number of adult fish returning to each area. This is called escapement. Managing for this goal requires understanding the return in real time and without relying on landings by commercial fishers to do so. Thus, Alaska runs a test fishery. This figure shows the gray bars, which are inshore catch plus escapement. The black line is the pre-season run forecast, and the red line is the in-season one. They use this to determine the peak and set escapement limits and harvest targets. Another example of a short lead forecast relates to the Maine lobster season. Recently, a statistical forecast has been operationalized for the seasonal start time in the Gulf of Maine. The opening is based on lobster growth and development, which is in turn influenced by temperature. A statistical correlation between temperature and development was used by Gulf of Maine Research Institute researchers and NOAA to set up a seasonal timing forecast that is updated weekly. This forecast is already being used to communicate to fishers, as for example shown here on social media. Because the forecast is based on a statistical correlation rather than a physiological model, it might benefit from updating parameters as new data comes in. This process of updating forecasting models with new information is often called data assimilation. Forecasting involves an iterative cycle of producing quantitative projections with uncertainty, collecting new data, updating estimates, and producing a new forecast. The updating process is where data assimilation comes in. As a side note, in fisheries stock assessment, this integration of new data is also known as integrated analysis. Data assimilation improves estimates of both model parameters and current state to reduce projected uncertainty. In practice, this can mean rerunning the estimation procedure for a forecast each time new data is collected to produce a new forecast. More formally, the iterative procedure can employ statistical tools, Bayesian state space estimation, and the Kalman filter. This statistical procedure starts with a rough estimate and improves the estimation of the location and underlying parameters as more data is gathered. These tools have been used in a large number of engineering applications, including the Apollo missions. The tools were developed in engineering and control theory and have been employed very successfully. The basic idea comes from the question of how to project a smooth trajectory, like a rocket's path, from noisy real-world measurements when we know the physical laws. For an example of data assimilation SE systems, we return to disease forecasting. This time we consider the H1N1 epidemic of 2009 in Singapore. This graph shows the course of the epidemic, the yellow points on the left, and a forecasted trajectory, the thin lines, based on partial data, the red points. The projected final epidemic size is also shown here on the right. Early on, by June 10th, the forecast projected an epidemic peak in late July, although greatly overestimated its magnitude. Subsequent updates assimilated observed data, the red points, and changed parameter estimates, which reduced the peak, although there was still large uncertainty, seen by the spread in the lines, around the projection. After the epidemic peak, the uncertainty was greatly reduced even around the projected final size of the epidemic. For short lead forecasting in SESs, it is possible to use statistical or process-based models so long as they capture relevant variation. It is easiest to forecast outcomes that aren't affected by unknown or unanticipated human responses and interventions. As the length of the forecast gets longer relative to the scale of process uncertainty, it becomes more important to include multiple models in the ensemble forecast. For repeatedly used forecasts, there is also the need to update estimates of the underlying model. Here, data assimilation can help. However, measurement of the forecast outcome requires care, especially if human and social dynamics are not modeled, and human responses or interventions can affect the focal outcome. An example of dealing with this issue was the use of a test fishery to manage sockeye salmon in Bristol Bay. We've covered a lot, so let's briefly review. Qualitative scenarios offer the broadest possibility and forecast the most apparent certainty. Quantitative scenarios promise a middle ground, but only when combined with the broad exploration of uncertain human responses can they fully explore the deep uncertainty in tightly coupled SE systems. Combined qualitative and quantitative scenarios are most appropriate when the purpose is broad exploration of the possible, when systems models are available, and when stakeholder interaction is possible to enable linking the qualitative and the quantitative. Finally, forecasts are most appropriate for projecting what is likely given the current state of policy and environment. Necessarily, these exercises work best over timescales that are short relative to the underlying socio-environmental processes, but their accuracy can be improved through iterative procedures like data assimilation. Thank you for joining this module on futures modeling. This is part of Succinct's video series on socio-environmental modeling, so please explore Succinct's other videos as well.